Hello, everyone. I hope you guys are doing great. So welcome to the lab of our ECS 388. So in this lab, we're gonna learn how can we use the embedded systems, how can we program the embedded systems, and these videos are gonna help you to learn and try to understand better how we can program our embedded systems or devices. So myself, Mahamadul Hassan, I'm currently PhD student at KU, and my lab is ASTHA lab, that is Assurance of Security and Trust for Human Hardware. And yep, you are welcome to visit our lab where we work on different security concerns of hardware, or you can say IC supply chain. So this is the overview of our video lectures. So at first, I'm gonna go over what is the difference between the low-level language and the high-level language, as we are going to use C language, that is a lower-level language, and we program the embedded systems using a lower-level language. So we are gonna try to understand how we are trying to understand the concept behind to use the lower-level language on embedded devices. Next, we are gonna try to grasp the concept of language processing system, where our source code is converted to a machine language code, and that runs on CPU. Next, we are gonna go through in details like how we can compile our source code, that is a C program, and there are different stages during the compilation, and we're gonna go briefly how each stage is converting our code from one 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 stage to other stage, and finally in the machine language code. Then we'll briefly overview of how that C program we wrote gonna execute in a processor or in a CPU. And finally, we're gonna talk about the memory organization, how memory is connected with our CPU, and how it efficiently collect all the data from the memory and do the operation. And the later part, we are gonna go through the most essential parts or the concepts that are gonna help you to complete your lab and try to understand deeply, and I mean, it will help you to understand the concepts of different, I mean, different part of your code that is gonna be given during the lab hour, and it will help you to eventually understand how we are programming a microcontroller and doing some specific tasks. So each lab, I mean, you are welcome to overview all of the labs, though some of the labs are already you guys are done with. But I would say, I mean, if you have any confusion, like what part of this code is doing for this task, this video is gonna be very helpful for you to understand that concepts. So uh, let's start. So we know there are lots of computer programming nowadays. We can hear about, for example, C, C++, Java, Python, or Rust. But if we want to categorize those programming languages, they're basically divided into three parts. I mean, we can categorize them in three categories in terms of abstraction level. By abstraction level here, we meant how this programming language is connected or close to the hardware, because we write a code that is basically a software, and eventually it converts to the machine code that's all binary and runs into our hardware, that is CPU, right? So yeah, we can do programming on, I mean, we can directly write code like machine code that's gonna be run on our hardware, but that's not efficient to write the code, because you have to understand a lot of hardware details to write that, right? So that's why, I mean, people, they developed these higher level languages to get rid of, to know the knowledge of the hardware. But as this course is all about the embedded devices, and we know embedded device is a very tiny hardware, so we need to at least know some part of the details of lower level languages. As a result, we choose C, because, as I mean, also the embedded devices support C. So with due respect, the low level languages that has literally no abstraction, I mean, uh, it is machine dependent. And the mid-level languages, I mean, for example, C is very close to the machine, and we can read the source code, as this is a readable format. But for the lower level language like machine language or the assembly language, it's very hard to read, because without the hardware information, it is very difficult to understand. And high level languages that has a very strong abstraction, we have, I mean, it is very comfortable to learn, for example, Python, and we don't have to think about the hardware at all. So you can see here, I mean, the hardware is closely connected to the low level languages. And for the higher level languages, you have to go through all this abstraction level to talk with the hardware, right? Next, as you guys are already know about the Python languages, I'm gonna I'm gonna discuss some of the distinct differences between these two language, that is Python and C. So when you write a code in Python, basically you write once, and that code can be run anywhere. And the Python code is, we run Python code through an interpreter, and that interpreter is basically taking our Python source code and also the input, and run each line in our CPU at runtime. On the other hand, C is a compiled language. I mean, we have to compile it first. So we write our source program, and we use a compiler to convert that source program to a executable code. And this is very specific to the machine. For example, for ARM or the x86 processor, there would be the different, version of target program. And with input and the final version of the compiled code, we are able to get the output from our source program. Python is yes, is definitely simple, and the readability is higher compared to the C. And C is a complex language, and also, I mean, learning C is time consuming. That's why it has a steeper learning curve. In Python, the memory management has been done automatically. So, I mean, the interpreter are helping us to reducing the manual efforts. for memory management. On the other hand, in C language, we can manually do the memory management, and that's why it became the one of the most highest efficient language that directly talks to the hardware, that directly talk with the hardware. And yeah, I mean, Python is more popular for its versatility. I mean, it has a lot of libraries to do data analysis and artificial intelligence tasks. On the other hand, C is in more system level language. We use it for embedded systems, or if our resource is so constant, but our performance is very, I mean, our performance is critical. In that case, we use the C languages. Okay, so now we're going to talk about the language processing system, how we how our C language basically converted to the machine language code. So we have our source programs. We wrote it in C, that is human readable format, and our code is then go through some preprocessor. So here in the preprocessor steps, this acts as a first stage. It prepared the code for further processing by subsequent components like compilers. And this preprocess includes all the header files like the function declaration, constants, and the data structure. Also, we have the macro expansion. I mean, we define some of the variables that gonna use uh, in the whole program's lifetime. And we have some conditional compilation things like, for example, if def and if and def. So all of this, I mean, preprocess has been done by the preprocessor. Next, we have the compiler. So after preprocess, our compiler take the source program and convert the program to the target assembly program. So in this stage, we call the tool that helps us to compile our code to target assembly program, that is assembler. And finally, from our assembly code using the loader, we got the machine code that is ready to run in our CPU. So here in the loader, loader is basically take the executable from the linker. So inside this loader, we have another tool that we call linker. So what the linker does, it take all the objects file generated by the assembler that contains the machine code, but lack of complete execution. For example, when we use a print function to print some line, that library is not initially present in our code. So linker, what it does, it links that print library machine codes with our existing machine codes and finally give it to the loader. And loader takes that executable from the linker and link the code to dynamic execution within the system's memory. And also the loader produce the absolute machine code. And after getting the machine code, we can actually do the reverse engineering. By reverse engineering here, I meant if we have a machine code, we can go backward to retrieve our source code, and that is also possible. So we have these two steps of language processing system. And you can see the intermediate files after each process. And this whole system we call the language processing system. Now, when we compile a C program, we call it a recipe, or you can also call it the compilation process. So, for example, we might have multiple C files, that is our source code, and as I already told you, it first goes through the preprocessor. So that preprocessor takes all the header files and finally generate a single file from all of these files. So these header files are basically have the necessary, necessary information to completely functionally make this code correct. After the preprocessor, we send our code to our compiler, and from the compiler we generate the object files with the help of assembler, and those object files are linked through a linker. So the linker has all the libraries uh, we initially wrote as we initially wrote inside of our codes, and it link all of these libraries with our object files, and finally generate a binary executable. And this binary executable is ready to run on a CPU. So this is a very fundamental concept, how we compile a C program. And this is very important to know when you are working with a C program. Now, let's talk about how a program executes in a CPU. So, as we already know, our source code C is compiled to a machine-specific binary code, and our compiler, what it does when it generates the machine code, it follow a set of rules. So we call those rules the instruction set architecture, or ISA. And that rule is defined by the machine or the processor architecture. For example, if your machine is x86 based architecture, the compiler will translate your source code to that specific machine code. If it is not x86 based architecture, for example, if it is ARM based architecture, so the rules are going to be different, because these rules are basically tell the hardware how it's going to process your source codes and will run onto it. So these rules are not like written by some software engineer. It is basically derived from the hardware. So these rules are basically the explanation of your CPU that consists registers, ALU, program counter, and a controller. So these components are the very basic base, very basic uh, components of a CPU, and with the help of these components, a CPU can run your source code. The CPU also uses an external memory to complete the execution of our program. For example, if we write a source code, you can see here we have a very simple source code, a while loop, and just the iterative addition of a variable. So we compile our source code, and we get this assembly code. And finally, this assembly code is converted to the machine code, the binary code, and we keep this binary code to our memory with the help of the loader, right? So in the memory, this instructions is basically sequence of our program, like a step by step what we are doing, what our program is basically doing. And here in the memory, this instruction is basically in a binary format, like it contains only 0 or 1, but for visualization to understand the concept, we just wrote it in assembly format. And after storing our code into the memory, now it's time for CPU to, go through each instruction and complete the whole program. So how a CPU can do that? So as I already told you, the CPU has the register, ALU, program counter, and the controller. So with all of these components, the CPU can run your instructions one by one. Our CPU is, as we can see, is connected to the memory, and to run each instructions from the memory. So this CPU first load the instruction to its register, and then it tries to figure out what a person uh, is doing this instruction, and from there it also figure out what data to use, right? So after that, it does all the computation, and after computing that instruction, it it go to the next instruction and do all those steps again and again. So as you can see here, this register is basically a 32-bit register. I mean, that can hold 32-bit of data here. So this 32-bit register is basically loading the instructions from this memory. So it can read the data from the memory and load it inside of its memory. And then with the help of the, the controller, it tries to understand what operation is basically this instruction, and with the help of ALU, it does the operation, for example, add, sub, or multiply, and then then it sends back the result from the ALU to the control register, and the control is again passing the data to that register. And if the case, I mean, we have to write the data from register to memory, it also does that. As you can see here, we have the read or write data. And after that, we go again to the next instructions and repeat these stages over and over until we finish our all of the instructions. So now we are going to talk briefly about how the register is different from the memory, right? So our memory is actually huge. I mean, as you can see here, I mean, the memory is very large. We can't fit it into our slide, right? So the instructions we have that that computes only in the register file. So the register file is very tiny, but also the fastest. And our memory, mostly data is stored in the memory, and memory is large, but it is slow. It is a lot slower than the register. So the register, what it does, it read and write continuously the data from the memory to do the operations or execute the instructions one by one. So now you can you can ask yourself why we need a very tiny register memory, uh, and uh, and why we are using the the large memory that is also slow. Why can't we use just only one memory and run the instructions, right? So first of all, these CPU registers, they are designed to be accessed at very high speeds because we want to run our instructions as fast as we can, and larger registers would take longer to read and write because of increased capacitance and the physical distances that the signals must travel. These would potentially slow down the processing speed. For example, uh, most of the modern processors, we have only, 32 or 64 registers. So as you can see here, we have here only 32 registers. And as a result, the registers are very fast because it can access the data uh, within its very short address space. Also, the registers and the memory, they both designed in a different way. Registers are made from the flip-flops, and each flip-flop is basically the collection of transistors. So if we increase the size of the resistors, means we are basically adding more flip-flops, which in turn significantly increase the number of transistors. This is not only require more physical space on the CPU chip, but also increases the complexity of the CPU design. And last but not least, if we add more transistors uh, in our CPU, that means there are more switching, more transistor switching, and more power consumption, because each transistor is switching from 0 to 1 and 1 to 0, and it is consuming a lot of power and generates a lot of heat. So this is a critical issue, as power efficiency and the thermal management are already significant challenges in the modern CPU design. So as a result, the CPU register is continuously reading and writing the data from the memory, and it has the latency, it has the delay of latency to read and write, but still the computation is very fast here because of the tiny memory. Now, as I already told you, our memory is very large and slow. So basically our memory, the RAM, is one-dimensional of array. So you can think of a large one-dimensional array of memory, and we have a lot of segments, and each segments that contains the 8 bits of data. So you can see here, we have a lot of segments, and each segment has the 8 bits of data. Depending on the width of these bits, as you can see here, if we have 32 bits of data fit into this register, we have total 2 to the power 32 possible combinations to access the memory. So if it becomes 64 bits, we have to design such memory that is used, but in a physical world that is not possible, because 16 exabyte is a huge number. You can calculate by yourself. So because of the hardware limitation and various factors, we can go up to 2 to the power 48, that is 4 petabytes. Now, as we know, we have, if we consider 32 bits computer, we have total 2 to the power 32 minus 1 address space if we start from 0. And we have 8 bits of data in each segment or each address space. And now in our register, we know we only have 32 registers, and for 32 registers we just only need 5 bits to represent those addresses of registers, and each register can have 32 bits of data, right? So as you can see, to fill a register, we need 32 bits of data, and we need 4 memory locations to fill a register, right? So in terms of filling a register, this is very inconvenient because we have to come again and again. I mean, we have to come 4 times here to fill a single register space, right? And also, if we have like 8 bits of memory, we have to deal with a huge address space that is 2 to the power 32 minus 1. So how can we, is there any way we can directly read the 32-bit memory at one, at once, and fill the register with that 32 bits of memory? Yeah, there is one possible solution. So instead of this 8 bits of memory, now we have the word aligned view of memory. That means we have now we have in 0 address space, we have total 32 bits of memory, that is 4 bytes. And the next address is basically the addition of 4, because we are skipping 1, 2, and 3, and we are directly jumping to the 4 and loading this 32 bits all at once into the register. So this was our byte addressable view of memory. Now we have the word aligned view of memory, and as a result, our address space is reduced by 4, because previously we had 2 to the power 32 minus 1. Now we are only considering 2 to the power 32 divided by 4 address space. So yeah, this is more efficient for the CPU registers to load the data from the memory. So instead of loading 8 bits, we can now, with just only one address space, we can load 32 bits of data into the register. Now, if we represent our address space in hex format, so yeah, we have all the way from 0 to a huge number, and usually it is a better practice to understand the address space in hex format, because most of the cases you will get the address space in hex format. Now, as we are familiar with the memory organization and the difference between the register and the memory, now we can go forward with our lab essentials. So in the first lab, we have to practice some of the C programs, and we have to know how the C program works. So as a result, the lab 1 essentials is all about the basic C programming. So at the very beginning, I'm going to talk about the C program structure. So for example, if we want to print the hello world in Python, we know it is very straightforward. We have to just write a single line that is print hello world. And Python have the built-in functions that automatically, use these print functions and print this hello world uh, string. And we no need to explicitly mention like which library are which library file are the interpreter gonna use for this print function, right? So that's how straightforward Python is, but for C, it's not that much gonna easy. We have to define every library we are gonna use throughout the program. So if we want to use the printf function, we have to define this standard io.h library. So we can define a library in our C program using this include keyword. So yeah, this is the predefined library that helps us to print hello world string into a terminal. Also, in our C program, there will be always a main function, and we have to use this. That's how the C program works. So so you can basically say this int main and include library is a basic skeleton of a C program. And inside of this main function, we have to write our code like our specific tasks we want to do using our program. So in here, we are printing a string. And also you can see here, before our main function, we have to specifically declare what this function is returning. So here, this function, as we use the int, that means this function main should return an integer, right? So as a result, we know we are not dealing with any integer operation here. So we are just returning 0. That means we are return nothing. So this is the very basic structure of a C program. We have to always follow this. And we have the format specifiers for our C program. For example, if you want to print a number, I mean an integer, for example, here you can see we first declared the variable using a type that is integer, but in Python it is pretty straightforward. We don't have to declare the type, but here in C programming language, you have to specifically declare every variable type. I mean, if you don't declare the type of the variable, the compiler gonna give you error. So here our variable is an integer. And if we want to print the integer, we have to use this %d. And the way we can, print the number with the string using this format. So this %d is the format specifiers that is telling the compiler we are printing a number, and this %d gonna check with the variable type. So the %d is for integer, and it basically represents the short form of decimal, that's d. So d is for integers, %d. And for %f is for floating point numbers. We have to, if we want to print a string, we have to use the %s, I mean a variable string. If we want to print a hex number, we have to use the %hex, %x, and so on. So for print a single character, so character are usually just only 1 byte or 8-bit. We have to use the %c. For pointer, we are going to discuss it later. We have to use the %p. Next, now we are familiar with the program structure. Uh, let's discuss about the variables and the data types we have in C. So as we already observed, like we have the integer, we have also the floating number, and we can declare the type as a float, as you can see here. But once you declared one variable with the type, and if you want to, for example, for float type variable b, uh, we define the number, a floating number. But if you want to, for example, instead of this floating number, if you want to store a string, you can't do that in C here. But in Python, it's very straightforward. Previously, for example, the variable a was an integer, and now it's changed to the string. To change a type of a variable, we have to use different functions that can convert the types. And in C, we have total 3 data types, but the last 2 can be defined as the composite type. So the C language provides the primitive data types, that is integer, float, double, character, etc. And the composite data types are basically array, structs, and pointers. And the composite types are basically, we can create this data type with the primitive data types. On the other hand side, the Python has also a rich set of built-in types, for example, int, float, string, list, a tuple, or dictionary. And to be honest, Python's types are more flexible and provide high-level functionalities directly. So here we can see in our C language, we have total 32 keywords, and you can go through them one by one to understand what each of the keyword is doing. But you can see here the integer is one of the keyword, and like conditions if is also the keyword. Uh, in C, we have all the basic operators, for example, greater than, less than, or greater than, equal, or not equal. We have a logical and assignment operator in C. For example, this and is basically checking, it returns true when the both condition are true. For example, on the right hand side of this and there are one condition, and on the left hand side uh, there is another condition, and if the both condition are true, then it will return true. So yeah, I mean, this is very straightforward. These operators, you can go through each one of them and try to understand their operations. Besides those operators, we have some extra operator which is very helpful in C. For example, we have the size of operator. So this size of operator, as the name suggests, it returns the size of a variable. For example, uh, you want to create an array of all the student IDs, right? And the student IDs. For example, you want to create an array of 100 students ID, and the ID number is between 0 to 255, right? So we know, I mean, the default integer type can represent 32 bit of numbers, but here we know the IDs are only between 0 to 255, and to represent 0 to 255, we only need 8 bits, right? As we know, 2 to the power 8 is 255. So we, instead of int, we can declare a array as a character. So this array is can now have only 100 IDs, and each ID has size of only 8 bits, right? So this array should have the size of total 100 ID, and 100 into each ID is just only 8 bits or 1 byte. So it should be total 800 bits of memory, right? So if we want to calculate the size of this array, we can calculate it using the size of, as you can see here. So the size of the array is just, we can use this size of operator and just give the array name, and it will return the size. So here in that case, we have total 800 bits of array. So this is very useful to know how much memory you are consuming during the array calculation, because you can also consider using the int, but as you know, I mean, the int will take a lot of space, and you don't need that much space for to represent number only 0 to 255. And this size t is another keyword in C. So this is the type that has the maximum bit width. For example, this size underscore t is can be varied based on the machine. For example, if you have a 32-bit machine, so the maximum number you can have is 2 to the power 32, right? So this size t is basically check the maximum the maximum bit available. I mean, the this size t basically tells you the maximum size of a number you can hold into a variable. So in that case, if you have 64-bit of CPU, this size of array can store maximum a number that has 64-bit. Also, we have the bitwise operators in C. This is very straightforward, like how we do the shift operation. So we have the complement operator, we have the left shift and right shift operator. So this complement operator is basically flipping all the bits, for example, 0 to 1 or 1 to 0. And this left shift and right shift operator is shifting our number based on a base. So for example, if I gave 1 left shift by 2, that means we will add 2 zeros on the right hand side of our 1, because 1 is shifted by 2 zeros. The same thing goes for this binary right shift operator. So here, as I already believe you are familiar with the basic gates, I mean, the AND gate, OR gate, and the XOR gate, or the NOR gate. So we can also do the bitwise operation in C, and it's pretty handy for doing a lot of tasks in embedded systems. We're gonna go over it and tell you more details for the next labs. But here you can see here we are doing the bitwise operation. For example, 0 and 0 for the AND operation. The 0, if there is any of the bit is 0, it will return 0. And you can see, you can observe the output as for any 0 between x and y, the AND operation is written 0. So we can do like 4-bit bitwise operation too. So in the 4-bit, I mean, if our number I mean are more than 1 bit, so it will do bit by bit uh, operation. The first bit gonna be AND with the first bit with I mean, the first bit of y is gonna be AND with the first bit of x. So and so on. It will go from all the way to left to right and do bit by bit operations. So please check these calculations and make sure you understand how the bitwise operation is happening in this two table. Now let's talk about the pointer. So this part is the most important part for you, because the C language is basically a pointer-based language, and our labs from lab 2 to all the way to lab 6, we are going to use the pointer concept in our codes. So you have to understand how the pointer is working. Like basically we have to understand the code, like what this line is doing. So to do that, you have to understand the pointer operations. So as you can see here, I divided the pointer concepts into several sub concepts. So at the very first, let's try to understand how we can declare a pointer. So the first question is, what is a pointer? So pointer is a special type that can hold the address of our memory locations, right? So we as we already told you, we have in our memory we have segments, and we can access those data inside the memory through an address, right? So pointer is basically is a special type that can hold the address of ours, that can hold the address of our memory. So we use this asterisk notation to declare a pointer variable, and this notation indicates that the variable stores a memory address pointing to a value of a specific type, right? So here on the right hand side of the table, you can see here we declared a pointer to an int, because this pointer is holding the memory address of an integer variable. Now, as we know, our pointer can store the memory address, and we know our memory address hold a specific data or the value, right? So is there any way we can get the data from that memory address? Yes, that's called the dereferencing of pointers. So when we applied the dereferencing of pointers, uh, that is also using the asterisk sign. The asterisk operator yields the value that is stored at the pointer's memory address. Okay, so this might sound confusing. So let's go through this snippet of the code. It will help you to understand the point declaration and the pointer dereferencing. So here you can see we declared a variable a as the integer, and this variable a is holding the value 26. And we also declared a pointer. So to declare a pointer, we have to use this asterisk sign before the variable name. So here I gave the variable name as a PTR, but it can be anything, but you have to use this asterisk notation before the variable name. And then the compiler will understand, okay, so this is a pointer and it holds the memory address of a value, right? And the value, I mean, the location it is storing, initially when we declared a pointer that is PTR, it was storing a null memory address, I mean, a garbage memory address. But now, when we specified like we want to store the memory address of A inside of this PTR, we have to use this ampersand. So this ampersand in C language has a special meaning other than the AND operation. Please don't get confused with these notations. So if we use this ampersand before any variable, it is basically meaning that we are trying to retrieve the location of this variable. So here we are, in summary, we are storing the location of this variable A. I mean, the memory address of this variable A, we are storing that into the PTR variable. And if we want to dereference, the pointer, if we want to get back our value, we can create another variable that is the dereferencing value here, and we have to just use the pointer name and this asterisk sign. So this d value will have it will yield 26 here. So let's go through a more detailed way how it is working. So we have this single array of large memory, and we have those addresses, for example, 0x1, 002, all the way the highest address space. And this 26 is basically, in hex, it is 0x1a. So as you can see here, this value 26 is stored in the address 0x2004. And when we declared a pointer and stored the address of this variable A, as you can see here, this PTR is having the value of address of A. As you can see here, this A variable has the address of 0x2004 and have the value of 0x1a. And in the PTR, we are having the value of address. We are having the value of address A that is 0x2004. And as we declared a variable as a pointer, so our pointer has also an address, right? So as you can see here, the pointer that is storing or pointing to address space, we have 0x100 that is pointing to the address of variable A. So in our memory, you can see here, the 0x100A contains the memory address of A. Now, we can also have the function pointers. That means if we have a function, for example, here our function is something void, and the name of the function is function ptr. So here, uh, as I already I already told you, like we can have uh, the main function, or we can have any function in C, but we have to declare the return type. So here, as the return type is void, that means this function return nothing. So that's why there is no return statement in our code, as you can see. But previously, we for an integer function, we return the 0 uh, just because we that is our main function, and main function always start with the int. So it's basically, you know, the rule of C language. You can think you can think it as it way. Okay, so this void function has the before I mean, this void function, the name before the name, we have a pointer sign, and that means we are declaring a pointer to a function that is taking an integer and returning void. Okay, so if you use a pointer before the function name, uh, it basically telling the compiler this function is taking this function is basically a pointer to a function. That means it is pointing to a memory address that starts the function address space. So this function also is basically a set of instructions, right? I mean, this function, we are going to call them into our main function, and this function has also unique set of instructions, and this asterisk sign, I mean the pointer sign, is basically returning the very beginning of that instructions. I mean, it's pointing to the location of the very beginning of the instruction of void function. And we can also have the multi-level pointers. We have a pointer of a pointer. Uh, if we go our next slide, so here you can see we had a pointer that is ptr, and we have now pointed to a pointer. So basically, what we are doing, we are creating a multi-level pointer using the double asterisk sign. That means this variable pointer to pointer is having a address of another pointer. As you can see here in our memory address space, uh, our 0x100 have the memory location of variable A, and in the address 0x1008, we have the address of 0x100, that is point to a pointer. In the same way, I mean, we have to also use this and sign to retrieve the address of that variable. Yes. Now we have the array notation in the function parameters. So as we know, we can create an array with fixed size, but we can also create an array of uh, uh, we can also create an array we can also create an array using the pointer. For example, here the code that is taking uh, that is taking an array as a argument. as you can see here. And this array is created using the pointer. So we know the array is a 1D uh, 1D of a storage element, and by using the pointer, we can just point to its very first element of the array, and we can go through the next elements by just increasing, I mean, just increasing the accessing size of that array. So if we have an array that has, for example, 10 elements, so if we know the very beginning location of that array, we can iterate through 10 times. We just jumping or hopping through one from one memory to the next memory address spaces, and basically retrieving the data from that array. So let's go through in details how we can how we can observe an array as a pointer. So that's our goal here. So as you see here, we declared an array as a element of 4, and that contains value 10, 11, 12, and 13. So if you want to print this array, we can just only use the the first location of that array. And when we declared this array, so this array is a pointer, and we can use this array to return the very first address space of that array, just using this pointer sign. So if we know the size of our array, for example, here it's 4, and we can use the for loop to go through each of the array element and print the data of that memory locations, basically. So as you can see here, we have locations from all the way to 0x200 to 200C, and each memory address is increasing by 4, as we already observed that in our word aligned view of memory, like we increase 4 for each address space. So yeah, so the first element of the array located at 0x200, and the next elements so on the next addresses. And this is very efficient to to collecting the data from the memory, because the consecutive addresses contains your data. Also, we have different use cases of accessing the data using the array pointer. So we can use this vector format to access the data from the array, but we can also use like the the we can also use a different way of accessing the data. So this table shows you all the techniques to use the pointer array to access different memory addresses and their value. You might see different uses of pointer array in different codes, and it's very easy to get confused, but you can use any of them. For example, as we know, our array contains 4 elements, that is 10, 11, 12, and 13. And the address of these elements are 0x200 to all the way to 0x200C. So yeah, so this is the the hexadecimal representation of our memory address. And if we convert this memory address in the decimal format, we have this 8192. And you can see here it is increased by 4 in both places. And our array 0, I mean, in the vector format, is basically pointing to that data. And the location 0x200 can be, we can get this location by using this AND sign before the array. Also, if we have array, we can just add 0, 1, 2, or 3 to access this data instead of this vector format. This is also doable. For example, if we create a pointer that is pointing to the pointer array, we can also use that pointer to access the data from these locations. So also we can access different locations. I mean, using moving our array pointer from different locations. For example, if we want to know what value resides in this location, we can just we know this location is just 2 steps before of this current location, and we can just use -2 to access the data from this location. So as you can see here, this is very efficient techniques to collect the data from the memory. And all the techniques are doing the same thing here, that is accessing the memory location. So based on your preferences, you can use any of them. Now we have also 3 other use cases of pointer. We can use the pointer to allocating the dynamic memory. So dynamic memory allocation in C is used for various reasons, and it is one of the core aspects of the language that provides flexibility and control over how memory is used during the execution of a program. Here are some of the main reasons why the dynamic memory allocation is used. For example, if you have a data structure like an array, and you don't know the size of that array might be at the compile time, and the size of that array can be changed at the runtime, right? So dynamic memory allocation is necessary in that case if you don't know exactly the size of your data. And for instance, when reading data of unknown size from a file or the user, you can allocate the memory as needed by using this dynamic memory allocation technique. Also, the dynamic memory allocation technique is helpful for efficient memory uses. A static allocation reserves a fixed amount of memory throughout the program life, which can lead to waste if the maximum allocated is not used, right? With the dynamic allocation, you allocate only the memory you need when you need it, and use it, and just you are reserving the other memories for some other tasks. We can do that using this keyword malloc. Here you can see, and we also use the pointer notation here to dynamically allocating the memory. And here we are allocating the size of 10 integers. So if we know the size of the integer is 32 bits, so here basically we are dynamically allocating 320 bits. Also, we can do the pointer arithmetic, as I already told you, to access the array elements. we can just add number like +1, +2, or +5 with our pointer to, access the element of our array. And also our function return types can be pointer. You can create a function that returns a pointer, and this is a very powerful techniques to, for example, you have a function of an array sorting, and in that function you just returning the array pointer, and after sorting the array, you are just accessing the data from that uh, from that pointer location. Also, you can use this type def. So type def is a special keyword. Is basically you're creating your own definition, your type definition. So for example, this int pointer you created. So this int pointer, next time if you use this int pointer you can use it as a type. So if you write, for example, int ptr a, you don't have to use this pointer notation, because you already declared this type as a pointer to an integer. So that was all for the pointers. So I hope this was helpful, and I'm requesting you to go through these slides again and again, and trying to understand these pointer concepts. And also we have some important intuition of how the C language is a pointer-based language. As I already told you, I just told, like, C language is a pointer type language. C language is a pointer language because the most of the functions you're gonna use in C, either they take the arguments as a pointer, or the return, those function returns the value as a pointer. So that's why you have to understand the pointer concepts very carefully. For example, this scanf is a user argument. It asks, it asks something from the user, and whatever the user is giving, it has to be a pointer to a character here. Also, there are functions that modify the data passed to them, typically require pointers to the data types they are meant to alter. For example, this string concatenation, that is string cat, requires the data as a pointer. You have to point to that location that has those data. It's gonna be, concatenate. Many memory management functions, for example, malloc, free, memcopy, and those other operations, they operate on the pointer. Also, here are very basic common standard functions that we use when we write code in C. And you can see here, most of the cases, the argument is they're taking as a pointer. So you can't avoid pointer in C language. You have to understand the concept of pointer. Now, for your lab exercise or homework, you have to work with some of the example problems, and to solve those problems, you need some understanding for some concepts. And basically, for lab 1 exercises and homework, you must know few concepts before jump into the code. So here we can see how can we interact with the user in C. To collect user's response, we have several predefined functions we can use. This function is already written for you. So we can use the scanf, or we can use the if gates, and these functions can read the data from the user. So there is one thing you have to understand, like when we declare a fixed size of a string as a character, we can do that is this way. So here, this string variable can have 100 characters, and each character is as we declared this variable as a character, that means we have max 100 we max have 108 bits of data we can store inside this variable. So if the user, for example, here in that case, they provide the input that is more than this size, the compiler will give you an error. Here, we just only declare this variable as a single character that is just 1 byte or 8 bit, and you can see here we have to use a space before this %c, because that's how it works. So this space before %c to skip any white space. And if you want to compare any character or string in C, you can only use this equal sign for just a single character. That's why you can see that this is correct, but this is incorrect. So this single quote is basically telling the compiler this is only 1 byte or 8 bit of data, and we are comparing it with this character string underscore C. But if you want to compare some string that is more than just 1 byte, you might use some different functions. We'll talk about that later. Also, you can use the if gates if you want to read the string of a line or a big text, and that is easier. So I will ask you to, as you are already familiar with the Python, you can do the same things using the Python to understand how these both languages are different from each other. Also, we need to understand some of the functions. We must know how type conversion works in C. If you know and use Python first, to be honest, you will dislike how C converts type. Type conversion in C is not straightforward like Python and needs deeper understanding. I would suggest you please practice as much as you can and ask yourself about different type conversion, and do it and practice those in C language. For example, here I showed you some of the conversion. For example, we can use this A to I, A to L, A to LL for converting strings to integer types. So this I means the string, integer, and this L means long, and this LL means long. And A to F, that means you're converting string to the float numbers. Yeah. We have another keyword that is printf. Sorry, not keyword. We have another function is printf to convert numeric values into strings. For example, if we have number 1 to 3 and we want to convert that number into a string, we can use a printf, and this is the way you can use that. We have also a string to long, string to unsigned long, string to long, and other functions that convert strings to their respective numeric types. So please practice these things during your lab to understand how you're converting the types from, for example, from string to integer or integer to string, etc. So now we are done with our lab 1 essentials. In lab 2, we're gonna talk about our microcontroller that we are gonna use for the rest of our labs. Yeah, thank you.